In this video, we're going to take a look at how to measure the absorption spectrum of the compound iron 3 thiocyanate, FeSCN2 positive. To do that, we're going to use a device called a spectrophotometer to shine light of different wavelengths, and you can see we're using wavelengths from 400 nanometers up to about 600 nanometers. We're going to shine that light through a solution of the compound FeSCN2+. Now we're going to form the compound by mixing Fe3+ aqueous with thiocyanate SCN- aqueous, and that'll form a reddish-brown complex ion, the iron 3 thiocyanate, FeSCN2 positive. Using the spectrophotometer, we'll record the percentage of light being transmitted through the solution. Then we'll convert that using the formula absorbance equals 2 minus the log of percent transmittance. We'll convert that back to absorbance readings. Now, a spectrophotometer is about a $1,200 instrument, which is really a fancy version of the colorimeters that we're more used to using with the handheld computer devices. A spectrophotometer like this one is called a Spec 20D digital. It has a knob on the top here that you can use to select a particular wavelength. And so right now, if we look at the display, we're using a wavelength of 400 nanometers. It has a sample compartment also on the top. The sample compartment, I can lift the lid, and I'm going to insert a glass cuvette in just a moment that has distilled water in it. Okay, distilled water we're going to use because our solutions are made with water. When the lid is closed, light can no longer get in from the outside. Right now, with nothing in that sample compartment, we want the percentage transmittance value, which is right now negative 3.8. It really should be a 0 right now. So on the front of the Spec 20, there's a dial, a knob that says set the 0%. So by turning that knob, we can adjust the reading at the top. Instead of negative 3.6, we can make it say 0. So I'm going to do that right now when there's nothing in the sample compartment. Now, it is a digital spectrophotometer, so you don't have to be neurotic. If it's negative 0.1 or positive 0.1, that's essentially 0. So right now, it's ready to go. I'm going to open the sample compartment, and I'm going to grab a cuvette that's been wiped dry and wiped free of fingerprints. This cuvette is actually a rather expensive one. It's made of quartz glass, optical quality glass. It's much higher value, much better than the plastic cuvettes that we use with our colorimeters. There's a white line on the front of it, near the top. That white line tells you how to orient it when you're placing it in the sample compartment. You want the white line to always face forward. There's also a dot on the front of the cuvette, that white dot. When you're filling the cuvette with a solution, or in this case with distilled water, you want to have it filled up to that dot because the light will then will pass through the solution, or in this case the water, when it's below that dot. So I'll slide it into the sample compartment and then close the lid. And right now, I want the spectrophotometer to think that there's nothing in the sample compartment. I want it to ignore the distilled water. Right now, it's giving me a really high value for the transmittance. So what I'm going to do is set that artificially to be 100%. In other words, I'm going to tell the spectrophotometer to think that all light transmits through distilled water, so it basically is ignoring the distilled water. To set the 100% value, I'm going to use the second knob that's on the front, the one on the right, which is labeled 100% T, and by turning that knob, we can set the reading here from 137%. I'll turn it down until it says 100%. And one more time, when it says 100%, then basically the spectrophotometer thinks that all the light is going through the distilled water. It's going to ignore the light that is normally absorbed by water. Okay, so there we have 100%. Now I'll remove the distilled water cuvette. I have a second cuvette that I've already tested also with water, and it has the same reading as the first cuvette. So the second cuvette I'm going to use to hold my sample, and I've checked that it has the same transmittance values so that I don't have to apply any kind of correction values. Now over here we have beakers that contain test tubes with 10 mils each of our solutions. The left one I've actually mislabeled. It should be 0.002 molarity iron 3 nitrate. So in there you can see it's essentially a colorless solution. It's very dilute. Iron 3 plus is in there. The test tube beside it has a very dilute solution of potassium thiocyanate, and it's also a colorless solution. I'm going to mix these two solutions, and when I mix them, you're going to see the compound, the iron thiocyanate compound, formed. So let's pour one into the other, and do that carefully without spilling. And because the concentrations are so dilute, the compound that's formed, the reddish-brown compound, is a very pale orangey color, orangey-brown color. Now I'm going to pause the video. I'm going to mix this solution by pouring it back and forth through two test tubes, and then I'm going to rinse the second cuvette, the sample cuvette, 3 times with the solution, and then dry the sample cuvette and wipe off any fingerprints using one of the Kim wipe tissues. Alright, so I've now rinsed the cuvette 3 times with the sample solution, and I've wiped it off as well. You can see it's filled up to the dot that's on the front. I'm going to take the sample cuvette and slide it into the sample compartment with its white line facing forwards. Close the lid, and you can see that it has a percent transmittance value of about 42% at the wavelength 400 nanometers. So I'm going to go over to my data table here, and beside the 400 nanometer reading, I'm going to write down the percent transmittance, which was 42.0%. That's relatively high percent transmittance, so a lot of light is traveling through because the solution was very dilute. So now I'm going to remove the sample from the spectrophotometer, and I'm going to close the lid so nothing is in the sample compartment. I'm going to go over to the wavelength knob and change the wavelength by turning that knob until we get a wavelength of 425 nanometers, the next one on my data sheet. So the wavelength is now 425 nanometers. I checked that the value at the percent transmittance is still 0, and it is, as it should be if nothing is in the sample compartment. If it had drifted, if it was no longer 0, then I would use the set 0% knob at this point to make it say 0% transmittance. So I'll put the distilled water back in since we've changed the wavelength. We're going to put the distilled water in again with the white line facing forwards, close the lid, and it should still read 100% transmittance. We want it to ignore the water. Because we've changed the wavelength, the percent transmittance is now a little lower. So I'm going to go use the 100% transmittance knob, the one that's to the right on the front, and I'm going to turn it until the percent transmittance says 100%. Again, a 99.9 or 100.1 would be fine. Okay, a little bit too far. So get it to say 100%. That's pretty good. 100. Well, come on. Go back up. There we go. Take the sample out of the sample compartment. Take the distilled water out. And this time put your sample back in. Again, line up the white line and slide it all the way down. Close the lid, and this time we notice that that less light is being transmitted through there. At 425 nanometers, only 27.4% of the light is being transmitted. So 27.4% is being transmitted. Now notice if less light is being transmitted, then more light must be absorbed. So we're going to find here that the absorbance values are increasing when our percent transmittance values are decreasing. Now I'm going to continue this. I'll do one more sample here. So I'm going to withdraw the sample from the holder. I'll close the lid again, the sample compartment. I'm going to change the wavelength to the next one on our data table, which was 435 nanometers. So 435 nanometers. And there we go. Check that it still says 0%. If it didn't say 0%, we'd use the set 0 knob at the front to make it say 0%. Now we'll open the lid, we'll put the cuvette that has distilled water back into the sample compartment, line up the white line, close the lid, and it should say 100%. Because we changed the wavelength, it doesn't. So on the front of the Spec 20, we'll use the Set 100% knob, the one to the right. We'll turn it until we get 100% value with just distilled water in the sample holder. Okay, so there we have it. We're up at 100% transmittance. Now we'll take out the distilled water. We'll replace it with our sample, and again, notice I'm holding the cuvettes only at the top because I don't want to get any fingerprints or smudges on them, which would obstruct light. So if we did touch the sides, we'd use the Kim wipes to wipe them clean. Close the lid and notice that the percent transmittance has dropped again. So from 435 nanometers, we're now at 23.6% transmittance. So 23.6 is what I'm going to record on my data table as the percent transmittance. So I'm going to continue this until I've got the data table complete when I get down to 600 nanometers, and then you'll convert all of my percent transmittance values with your calculator to absorbances. You'll take 2, subtract the logarithm, the base 10 logarithm of the percent transmittance value. So for example, 2 minus the log of 42, and that'll be the absorbance value. Use 3 significant digits in your absorbances. Then use your Excel or some other graphing program to make an absorption spectrum, a graph with the absorbance values on the y-axis and your wavelengths on the x-axis. Don't connect the dots, just plot the points, and then once you've printed your graph, use your pencil to sketch a line that goes through the data. You should find that there's a particular wavelength that the iron 3 thiocyanate absorbs best. That wavelength with the highest absorbance will be called lambda max, okay, the wavelength at which it absorbs a maximum amount of light. Now, just one last thing about using the spectrophotometer. You'll notice that on the bottom of the Spec 20D, there's a filter, and the filter has to be flipped when you change wavelengths from about 340 to 599 nanometers up to 600 and higher. So if I were to get to a wavelength of 600 nanometers, I would take this little lever here and slide it over. If I'm using wavelengths below 600 nanometers, I keep the filter to the left. Now that particular filtering device is not found on all Spec 20s, but on this one it is, and I'd have to worry about that if I was going to use a wavelength over 600 nanometers. I'm only going to go up to 600 nanometers, so I'm not going to have to switch that particular filter. So there you have it. I'm going to post the results for you, and then you'll be able to make your own graph. So I've just finished the last reading, and it's 600 nanometers. I actually did have to switch the lever at the bottom. I forgot that we'd have a value at 600 nanometers. But the percent transmittance was 89.8 for our sample. So there is the data that we've been able to collect. Okay, so you could pause the video here, and you could record the data from 400 nanometers up to 600 nanometers and the percent transmittance values. Just examining it with the eye here, we notice that the transmittance values fell and then they started to rise again. So the absorbance values would do the opposite. The absorbance values would increase and then drop again. So the point where it changed direction seems to be somewhere around 455 nanometers, give or take. Well, we're expecting then that lambda max is going to be somewhere in that region. So you'll do that you'll get a more accurate value again by graphing your absorbance values, 2 minus the logarithm of percent transmittance, versus the wavelengths, which are in nanometers on the x-axis. Sketch a curve through your data points and label on your graph the wavelength, lambda max, that has the highest absorbance. We're then going to use the same compound, iron 3 thiocyanate, in fact that particular equilibrium reaction, and we're going to measure the equilibrium constant. We're going to determine the equilibrium constant for that reaction. To do that, we're going to be using a colorimetric technique with the colorimeters, not the Spec 20, and we're going to choose a wavelength from the colorimeters that is very close to the wavelength for lambda max that we've just measured. Okay, so there we have it. The sample in the colorimeter. I'll just remove it and make just a quick note. The compound that we're studying here, the iron thiocyanate, this orange-brown compound, is relatively unstable. So when you're doing this experiment, you have to work relatively quickly. Okay, you wouldn't want to just work over the span of, say, a couple of hours or even an hour with this kind of compound. It'll decompose, which will affect its absorbance values, its transmittance values. If you were to leave the sample in the sample compartment for an extended period of time, then the spectrophotometer will cause the sample to warm up, which will speed up its decomposition. So basically, work quickly and methodically. The entire experiment here took me about 20 minutes to run through the entire spectrum like I did, from 400 to 600 nanometers. So one more time, there's your data. Go ahead and graph it and come back with your lambda max value for iron 3 thiocyanate.